Happy Wednesday, everybody. Let's program some computers. You should have an email with your midterm exam digitally returned, and the average was 78. So it seemed to me that the exam was like right in the middle of the level of difficulty. And we also emailed out draft letter grades. So we finished about 50% of the points in the class. So you still have a lot of opportunity to bump your grade up if you weren't happy with what you saw. So you've still got 50% of the points among the final P4 and P5. So there's a lot you can do to change your grade. Any questions about class logistics? Yeah.
I don't know if you talked about it, but is the median on Project 3 like lower than what it usually has been in the past?
The question was what was the stats on P3?
I saw it was 78%, but
It was like 70%, wasn't it?
78.
78 on P3. It was just a little bit lower than it has been in the past. Was there anything different about it this year? The deadline was pretty crazy. It seemed like more people got started late this year compared to previous semesters. Not real sure why. But that's just anecdotally. I don't have any hard data to back that up. All right. Any other questions? Yeah.
Representation of heat. I've seen it at the bottom of columns. I've seen it at the top of column. I've seen it represented as a big circle.
Representation of heaps. Like, why did different textbooks or like different websites online represent it with different pictures?
Or different instructors in 280. And this isn't a complaint. It's just
Or different instructors in each 280.
Yeah.
So on the one hand, there's the theoretical concept of stack and heap, and sort of getting it in your head that they're two different things and they're both in memory. And then there's the way of thinking about it that's more like the computer hardware. And like, well, these are actual addresses, and they have numbers, and some of those numbers are bigger than others, and somehow they're in a line. So that's how I end up with diagrams that like look like this.
So do we need to be too concerned about it as long as we understand?
Understanding the concept is the most important part. Knowing that they're in two different places in memory. That's the most important piece. All right. We are going to talk about linked lists today. Who's just heard the term linked list before? I'm going to tell you everything you need to know about linked lists today. We're going to implement an entire linked list between now and 5:30. So get ready. Oh, you're not ready. Yes?
Yeah, is this why the H file didn't make sense to me?
Is this why?
The H file, the project list didn't make sense.
Is this lecture the reason why the H file didn't make any sense when I read it? Yes. After today's lecture, the H file is going to make a whole lot more sense. So let's start with a little bit of computer science concepts. Is this the last piece of information we need to know everything we ever need to know? So project 4, the calculator driver, you don't need linked lists. You could make that out of a vector. To get the linked list thing right, you got to know this lecture. And then there's this thing called an iterator part of the linked list. Then for that, you need the next lecture. So you can get a lot of work done on project 4 before today's lecture, with today's lecture, and after. Okay. Computer science concept, sequence container. Sequence container means store the elements in order. This is a fancy computer science term for something we've already used this semester. Like built-in arrays, that's one example of a sequence container. Vector, that's another example of a sequence container. They are sequence containers because we could access the items in order. And the items, once they're in the array, they'll always be in the same order until you write some code to like take the elements away and put new elements in or overwrite them. So one option for sequence containers is to store them as next door neighbors in memory. So far, this is the only way we know of to store things in order in memory. So this is good because it makes for fast indexing. Here's an example of indexing. Here's another example of indexing. Just as a quick reminder, these are exactly the same thing. The compiler, when it sees this, turns it into that. Super fast. But there's some downsides too. Remember when we made the unordered set and we made it grow? That's like when we were starting to learn new and delete. To make it grow, if you have an array that has 4 items and you want an array that has 5 items, can you just add a slot and glue it to the end? No. You got to make an entire brand new array with a larger number of slots. And then you can copy the items and put a new one in the middle. So these are 2 things that are downsides of contiguous containers or array-based containers. One of them, if you want to increase the capacity, you got to make a brand new array. Second, if you want to put something in the middle, remember how we had to do that unsquish? And unsquish took a loop, and the loop took time, and we had to copy a bunch of stuff. Those 2 things are slow. So inserting in the middle really sucks with an array or a vector. Let's think about other ways to store sequences of items. So what if we didn't have contiguous memory? In other words, what if we said, all right, you guys are in order, but you don't have to be next door neighbors in memory. Instead of a pointer like arithmetic telling us where the next item is, let's just store the locations with pointers. So we are not going to do it this way. Instead of next door neighbors, what we're going to do, each piece of data is going to have 2 parts. The thing we care about storing, and then a pointer. And the pointer will tell us how to find the next piece of data. And then that piece of data will tell us how to find the next piece of data. And then and it's turtles all the way down. That's a recursion joke. Okay, we'll learn about recursion in the future. So each piece is called a node. A node is another computer science term. And let's use a struct to represent each node. So now we're going from computer science concepts to C++ implementation details. So let's dive into the details. We're going to use this implementation, a node struct that has 2 pieces, one for the data we want to store, and one is a pointer to another node. Notice how node can store a pointer to itself inside of itself. What? I'll let you chew on that for just a second. All right. On a 64-bit computer, how many bytes does it take to store a pointer to an int? How big is an int? 4 bytes. How big is an address? 8 bytes. So how big is a pointer to an int? 8 bytes. All right, how big is a pointer to a double? 8 bytes. How big is a pointer to a chicken? 8. How big is a pointer to a node? 8. That's how the compiler can get away with this. Because it's like, all right, whatever, it's going to be 8. Okay, here you go. Here's your 8 bytes. Are you happy? And we say, yes, we're happy. So you could template this thing, and that's what you'll do in the future on your project 4. I'm going to keep it simple today, and we're only going to use, we're going to make a list that stores only ints. How does the node point to itself? I think I misspoke. The node doesn't actually point to itself. It points to another node that's the same type. So it points to a neighbor that looks a lot like me.
If it really wanted to, could it point to itself?
If it really wanted to, could it point to itself? Sure. Can a pointer point to itself? Oh, well, I don't want to get into that. Never mind. All right. So this is called a linked list. Today, I'm going to stop using those stack diagrams that were all in order, and I'm just going to have like abstract art of memory. Because with linked lists, it doesn't matter exactly where they are in memory. What matters is that the next pointer points to another node, and that node points to another node, and that node points to another node, and then eventually we get to the end. So how did C strings know that the C string was at the end? What was the computer science term? Sentinel. And what was the C++ implementation detail? Null PTR, aka the number 0. So that I'm using the same trick here. I'm using a sentinel character. So again, computer science term, sentinel character, C++ implementation detail, the number 0, or null PTR. Questions so far?
Did you guys just come up with datum, or what's that?
Did I come up with datum? I mean, I just looked it up in the dictionary.
Is that an actual word? I don't know.
Yeah, it's singular. Okay, this is something that you all need to get as computer scientists. Thank you for bringing this up. Is that plural or singular? It's plural. So if I called this thing data, it would be kind of like wrong English. And it's really important that our computer programs have proper English. That is actually not true. So one piece of data. And then next is the next pointer. More questions at this point. Could you put 0 or null PTR? In your code, you could use either one, and you'll see me do that later in lecture. All right, so we've got a representation for one node in a linked list. That's what I talked about on the previous slide. Now we need a representation for one entire linked list. So we're going to call that class int list, because it only holds ints. To keep track of a linked list, I don't need to store all the stuff. I just need to store a pointer that tells me how to find the first thing in the list. Once I've found the first thing, can I find the second thing? And once I found the second thing, can I find the third thing? Blah, 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 blah. So that's why my representation has only one member variable, and it's a pointer. So this is now my abstract art representing the list 1, 2, 3, 4. We need a pointer to tell us how to find the first element.
So why do you need a class if you only have one member?
Why do you need a class if you only have one member? Because we're going to put lots of functions in. We're going to put in all the functions to mess with the list so that the other programmer doesn't have to worry about all these nodes. So let's look at the representation invariant. Let's look at what is a sanity check for our member variables. So first, remember that's the pointer inside of the list class, not the pointer inside of the node struct. It's either null, that's an empty list, or it points to a valid node. In the last node, we use a sentinel character. Next is always null. That tells us, hey, you're at the end of the list. You should stop. And then for every other node, next points to another node. I should add something to here, something that gets tricky. There are no cycles. So don't do that. So now we're going to implement some member functions. We need to create a new list that's empty. That'll be our constructor. We want to find out if there's anything in the list so we can test if it's empty. We want to grab the first element. I should actually call this the first datum. I want to add stuff to the list, and I want to remove stuff from the list. Now here's something about a list. The one we do in lecture today is a simplified version of a list. You can add to the beginning, you can remove from the beginning. That's it. The one you write in Project 4, you can add to the beginning, the middle, or the end. So here's how we use our int list from the outside. So imagine you read this h file, intlist.h, and you trusted that somebody else had implemented it correctly, this is what you could do. You could create an empty list represented like this in text. Then you could add 1, 2, 3, and then you can print one item from the list. That's front, like this. And then you can remove it all with pop, and then find out if there's anything left. Hey, it's empty. True. From the outside, like the other programmer who's writing the calculator in Project 4, writing a main function that uses the linked list, do they need to know about the node type? I'll give you 30 seconds to think. Okay, what do you think? Does code outside of the int list class need to know about the node type? No. With the code I wrote so far, could this code access the node type if it wanted to? Yeah, because I just put them at the top level of my file. So if you can access int list, you can access node. How could we fix that? So this computer science concept, as a reminder, it's called information hiding. In C++, we use private to get the job done of information hiding. And in the past, we've used private to make member variables inaccessible. We can also make a custom type inaccessible. Are you with me that node is a custom type? And we don't want other programmers to know anything about our custom type. So we're going to put it inside the private section of the int list together with the first pointer. So this is a variable, and this is a type. There's a difference. So true or false, when I create an int list object, it has storage for a pointer. True. True or false, when I create an int list object, I get a node value as part of the object. False. The reason why it's false is because this is not a member variable. Type, not variable. So this is like we're telling the compiler, when we make nodes in the future, here's what we want them to look like. And by the way, only int list member functions can make node objects. More questions? Is that because you need to initialize the type? So the reason it exists at all is because we need to use nodes. Now the choice is, do I put it here or do I put it here? If I put it here, it's accessible to any code. If I put it here, it's only accessible to members of the int list class. And we already agreed that we don't need access to this thing from the outside. Yeah. Can subclasses of int list use node? To answer that question, we'd have to go back to the rules of private, protected, and public. So subclass, is it allowed to touch private things? No. If it was protected, could it? Yeah. As an aside, it's quite uncommon to use inheritance together with containers. It would work, but containers are much faster when they use templates instead of inheritance. So let's implement the constructor. This code is the same as the previous slide. Now I've added a public section to my int list class, and I'm going to implement the constructor. I need to set my member variable. First, there's only one member variable. We're going to initialize it to null PTR, aka 0. So that means if I write this code, I get this memory diagram. Okay, let's move on to empty. We're doing the short functions first. So empty, let's go back to the representation invariant. What do I need to check to find out if it's empty? So we'll check for this. We'll check if first is null. If first is null, that means there's no nodes, which must mean it's an empty list. So here's how we check if first is null pointer. This list is empty.
Is null pointer a reserved word?
Is null pointer a reserved word? Null pointer is a reserved word in C++ 11 and later. All right, now we're going to do some more interesting code. This is 1 or 2 lines, and I want you to implement this function and use an assert statement to verify the requires clause. Then we're going to spend more slides explaining what's going on with that reference than we will actually implementing the function. So I'll give you a couple minutes to implement this, please. All right, let's take a look at this function implementation. So first thing we'll do is check the requires clause. Remember, requires that the list is not empty. Hey, we just wrote a member function to do that. So let's reuse the member function and make sure that the list is not empty. So are you with me that looking at the first item in the list, the front of the list, makes no sense if the list is empty? You can see that you can think about this intuitively, and that makes sense. You can also think about it in code, and it also makes sense. If the list were to be empty, what would the value of first be? What would the value of first be in an empty list? No, agree. And what happens if you do you agree that this does a dereference? What happens if you dereference a null pointer? Crash. Segfault. Naughty things. Undefined behavior. All right, so now let's talk about this line of code. What is the type of the thing in the red box? Int. What is the type that this function returns? Reference to int. Is there a problem? They are different. Here's something that's a little tricky that you might not have thought of before. Has anybody written a swap function before? Or passed by value something like this? So you can do int x, and then you can call swap x with no extra syntax. So it's like value to reference. We're doing the same thing here, value to reference. The compiler seamlessly converts between values and references. So why bother doing this? Why not just return a good old-fashioned copy of an int? Here's why. We can look at the thing in the list, and we can also modify the item in the list. And this is intended behavior for a list. So we're going to create a list. We're going to push an item into the list. Then we're going to print the item in the list. No surprises. It prints 1. Now, here's where it gets fun. Is this going to change the original value of the datum? Well, we can answer our own question by looking at the next line of code. When I inspect the next value, I see that it has indeed changed. I changed the original. This is possible because front returns a reference.
So would we get an error if we put ampersand before first statement? Like, you said the compiler does it automatically for us. Like, so do we just not need it?
Oh, your question was, what if we were to do that? Let's examine. Let's go methodically. All right, we know that the type of this is int. So what is the type of this? Pointer to int, or address of an int. Does that type convert to reference to int? It does not. So this example wouldn't compile. If I were to add that ampersand, it wouldn't compile. Because you'd have a pointer, and a pointer doesn't convert automatically to a reference.
Since we just want to use this function to inspect, why is this intended behavior so you can modify it using an
Why is this intended behavior? Because the designers of the standard template library list said, hey, let's be able to modify this stuff in a list.
But do you have a function for that? Push front.
Push front adds a new item to the list.
Oh, modify.
This one modifies an item that's already in the list. Those are two different things. So let me explain a second time with some extra code. So we're going to create a list. We're going to push something into the front. Then we're going to make a new variable. I can make a reference variable if I want to. We've done this in the past. Does this make a new object? No. Does it make a second name for an object that already exists? Yes. So x is a second name for datum. Which datum? That one. So no surprises when I print x and I get 1, because remember I put a 1 here. Then when I do x equals 17, that says, all right, go find the place in memory called x and put the value 17 there. Is that a copy, or is that the original object in memory? It's the original object in memory. I'm modifying it. And then when I print x, I get the same value. And I would do the same thing if I did il.front. I get 17. This is one of the trickier things to understand.
Every time you modify x, you call that function.
Every time you modify x, is it under the hood calling the function? No. It's like for the rest of that scope, we have a second name that we get to use for that piece of memory.
You could essentially do the same thing with a pointer, right?
Could you do the same thing with a pointer? We could do something really similar with a pointer if we did dereferencing. If we got our ampersands and stars right, we could achieve the same result, and that's how they did it in C. And then references came along in C++, and everybody was like, woo, we don't have to use so many stars. Okay, so next let's implement the push front function. We want to insert an integer, and we're going to start off with the first field points to the current list. The list might be empty, the list might not be empty. So the first thing we need to do is create a new node to hold the new item. We'll keep track of where it lives by using a local variable. Any questions about my starting picture? Then let's write this function line by line, and I'll modify the picture as we go. So now we need to set the datum field in the next field inside of our new node. So I take this and I copy it over to here, and I take this and I copy it over to here. Everybody good? So now I need to update the member variable called first inside of the int list class. So the int list object is here. It's got a first member variable, and I'm going to set it equal to p. So now first points to the same place that p points to. Then p goes out of scope. It's gone. And my linked list looks exactly like it should. A linked list with one item in it. Okay, now it's your turn. Please draw two diagrams for this code. One with the abstract art and one with a memory diagram that has the stack and the heap. So let's start with our abstract art. I'm not gonna do every single node. We'll start with this list, and we're gonna have to insert do the last one. Notice that if you push 3 and then you push front 2, you end up with 2, 3. So lists have this reversing property because you keep on adding to the front instead of adding to the back. All right, so let's say we're going to insert a 4. So the new element we call new, and we get this. Then we patch up the pointers, and we make the new item point to the old front. Then the first pointer, does it point to the first thing anymore? No, it points to the second thing. We got to fix that. So then we make first point to the first thing. All right, so there is our abstract art version. Now let's look at the memory version.
How does the node that's holding 3, based on our current implementation, why does next have 0 for null PTR? How did that get?
So the question here is about the sentinel value at the very end, specifically this right here. Why is that 0 when in our code, way back, we make it null PTR. Null PTR is a very fancy word for 0. That is why. If you look at the value in memory, null PTR is 0. Okay, more questions. Are you ready for memory diagram with stack and heap? Let's do it. So this is more specific. It's got the same information, but it's more specific about exactly where everything is. Notice that IL is a local variable. Local variables go on the stack. There's only one member variable that lives inside of IL. It's the pointer called first, and that pointer points down to the heap, and it points to the node that is at the front. The node that's at the front then points to the next node, which points to the next node, which points to null PTR. Is this the only correct answer to my problem? Is this picture the only way to draw it? Nope, we could rearrange them. As long as we follow the pointers and we get 4, 2, 3, then it's valid because it matches 4, 2, 3.
Why did you put no PTR inside the heap?
Why did I put null PTR down below the heap? Because null PTR is an address. That address is 0, and the 0th address is way down below at the bottom of my diagram. The big addresses are at the top, the small addresses are at the bottom. So there are Linux programs you can use to dump memory. There's like in GDB, you can dump everything that's on the stack in the heap, and you can see exactly what the addresses are. And those addresses, you could look at a diagram like this, and you could rectify that dump of your program's memory segment against this picture. Will we have to do that for project 4? Depends on how many mistakes you make with your pointers. Let me pause and give a hint for project 4. Draw pictures. Draw them. Draw the picture. It's surprising how hard it is to get the pointers right. If you draw the picture, then you can make your code do what the picture says. By the end of this lecture, you'll all be able to draw pictures that are correct. All right, before we do pop front, I think we need a break. Let's take 5 minutes. All right, let's get back to our list. I have a lot of pictures to show you. So let's do pop front, and we're going to do it again with pictures. Pop front removes one item from the list. So if we're removing stuff, it makes sense that requires the list is not empty. And because we're really careful coders, we use an assert statement and we verify the requires clause to tell us right away if we made a mistake. So we'll check that it's not empty. Done. So now let's move on. What? I already made a mistake. Well, what's the mistake here? Do you agree that we want to make first point to the second thing, and the second thing is first point to next? Okay. And do you agree that we want to get rid of the first node? Oh, after that. Oh, okay. So let's do that. I'll take your suggestion. We switch them. Uh-oh. You know, this is going to be on the final exam. Yeah.
Make a temporary pointer.
Make a temporary pointer. I love that idea. Let's call it victim. So basically the idea, we want to get rid of the first node, but we also want to use the first node to figure out what the second node is. So we'll make a local variable to remember it called victim. So we've got this victim that points to the first node. Then I advance the first pointer. That gets me to first, now points to the old first, or the old second. Now I can delete the victim. Okay, we're good. So let's do an example with this code. So here's all the source code. We're going to start with this list, and we're going to call pop front. So step one, we get a victim pointer that's a local variable, and it points to the node to be removed. Then we move the front pointer, this guy. Notice that we needed this code right here in order to do this. That's why I couldn't just delete the first item in the list. We need information from our victim first. So now that we're done with it, then we can call delete. It is removed from the heap. It can be recycled and reused in the future. And the victim pointer goes out of scope on this line of code. See how much easier it is with pictures? Just draw the picture when you're writing your project. Most of your bugs will come from not drawing the picture. I'll give you another hint. Linked lists are a good time to have bugs in linked lists is, let me just start over. When you're thinking about how it works, think about a list with 0 items, a list with 1 item, and a list with more than that. So three pictures actually. And make sure that it's going to work with all 3 pictures. Empty, 1, and more than that. Oh wait, I could write unit tests for that. Oh wow, that's a really good idea. Okay, if we had a single element, oh yeah, test 1. Okay, yeah, let's test 1. So we start off with a list like this. It's got 1 item. We call pop front. We get this victim pointer. Then we slide it over to whatever next was pointing to, which is pointing to null pointer. Turns out in this case, our code still is correct, because we really wanted first to point to null pointer. When you start with a list that has 1 item in it and you call pop front, you end up with an empty list. An empty list looks like that, where first points to 0. Victim goes out of scope, and this is what we want, with first pointing to null PTR. Yes?
So like, I mean, I'm sure like
I'm sure datum is in there somewhere.
But like we like deleted the one that had datum.
But we deleted the one that had datum. I don't understand.
So where's datum?
Where's datum?
Like in the new first or the new first. Yeah.
Oh, okay. So I think the question was where's datum? So what is the type of this object? Int list. Is int list the same type as node? They're different types. What's inside a node? A pointer and an int. What's inside an int list? A pointer, that's it. I think that's the tricky part to understand. We have two types here.
On slide 36, where does victim point to?
On slide 36, where does victim point to? So victim points to a node that lives on the heap. Which one? Whatever address this is. It still lives on the heap. We haven't called delete yet. Does that answer your question? Okay. Yeah. Isn't node a type within int list? So node is a type, int list is a type. There's only one kind of function that's allowed to use the node type. Int list member functions. Other than that, the normal rules apply. We're just restricting who can create nodes. We're not changing the rules about where they go in memory, and we're not changing the rules about like what goes in a struct and what goes in a class. So remember when we did traversal by pointer? And everybody was like, oh, this is so hard. So now we got a bunch of pointers. And in the past, we had next door neighbors. So pointer arithmetic made a lot of sense. It didn't make sense, but now it makes sense compared to this stuff. Is the next door neighbor trick going to work anymore? So is pointer arithmetic like we used it in the past, is that going to work anymore? No. Okay, use that what not to do hint to implement this print function, please. Yeah.
Create like
So if this is what our list looks like to start here at the top of the slide, we want to visit each node. So I can use a pointer to do that. We'll call it I. So I've got an object in my program now called I, and I points somewhere. Where's the first place I want it to point to? This thing right here. So we can make it point to first. Carry on.
Better just use a while loop.
See what kinds of crazy things we're about to do with this for loop. All right, so are you with me that this happens at the very beginning before the loop actually gets going? Okay, next we need to check, how do you know when to stop? Or, so let me rephrase that. How do we know when to keep going? Well, I is not equal to this thing, right? So null PTR. Will this compile? Yes. Will it find the next door neighbor in memory? Yes. Is the next door in memory anything we care about at all in this computer program? No. All right, so there it is. So how do are you with me that somehow we need a new value for I? And somehow we want the picture should look like that, right? How do I find this? I next. But wait, that's not a plus plus. I'm throwing a tantrum. Because for loops are for plus plus. For loops are for whatever you want. Just the beginning, when to keep going, and end of every loop. That's all a for loop is. Syntactic sugar. You could do this with a while loop, and that would be equally correct. And then we can do cout, I, arrow, datum. Boom.
Why do we keep going when I is not equal to null PTR?
Why do we keep going while I is not equal to null PTR? I like this question. So while I points to here, do you agree that it points to some valid node somewhere in memory? And that node has an address. And that address is some number that's definitely not 0. Is that address true or false? All the addresses are true except for 0. So yeah, so are we good so far? All right, and then I move my pointer, now points here. Do you agree that this points to a valid node? Yes. Does that node live somewhere in memory? Yes. Is the address of that node some big number somewhere on the heap? Yes. Does that big number evaluate to true or false? It evaluates to true, so do I keep going? Yes. Until eventually I is 0. Eventually I will be 0 when you go to this. That's when it stops.
But doesn't I point to the node itself instead of the actual?
I points to a node, and eventually, so imagine I points here. What is the value of I arrow next? 0. Okay. So then the loop comes back around and it says, oh, I not equal to null pointer? False. And it stops.
But isn't null pointer by itself? I can never equal null pointer itself. I arrow next.
Can I, so if I do this, will I kick out of the loop or will I try really hard to do that? I'll kick out of the loop.
I just don't understand how I can equal 0 because I points to the node, not the node's next value.
But in the end, it's no point. You'll eventually point.
So I have a question for you. What's at the end of the rainbow? No pointer. So now let's talk about the big three. Do we need the big three? That is my question. I'll give you a minute to think. And I really care about the answer why, because the answer why will help you get this right if you have something like it on a final exam or you're working on a 281 project and you're not sure whether or not you need to use the big three. All right, I will not ask you who got it right. Do we need the big three? The answer is yes. Okay, why? Because we use new. Most of the time, that's the right answer. So we're getting a clue in the right direction. There's a little bit more to it. It has a member variable that points to dynamically allocated memory that was allocated by int list. So here's the way to remember it. Int list made the mess. Int list must clean up the mess. So not every class that calls new or not every class that has a pointer automatically means big three. What matters the most is if the class made the mess using new, the class cleans it up using delete. So clean up your own mess. Kind of like college roommates. Oh wait, college roommates don't clean up their own messes. So here's what we need each function to do. The destructor should remove all the nodes. Okay, that makes sense. The copy constructor should initialize the member variables and then copy all the nodes from the other list. The overloaded assignment operator should remove all the nodes. Wait, remove all the nodes. Why? Because if you do like A equals B, you're going to like squash all the nodes in A and then make new ones. Otherwise, you have a memory leak. Yeah. And then copy the nodes from the other list. Hey, there's something in common here. Last time we copy pasted some code to get this job done. Today we'll write two member functions, like private member functions, and then we'll use those private member functions to implement the destructor, copy constructor, and the overloaded assignment operator. I'll give you a minute to chew on this. Are you ready to push all and pop all? So we're going to make these private member functions because it's our list and we can do whatever we want as long as it doesn't affect the public interface. We've already got a function to remove one node. Let's just reuse it. So while it's not empty, throw one away. When will this stop? When it's empty. Okay, great. Done. Was I too quick? Can I answer any questions? Is there a faster way? Sort of, kind of, a little bit, just a little bit. But let's not get into it. This is worth the simplicity. We could make a for loop that called delete. That'd be something like that. But we need a victim so we don't like get our pointers crossed and stuff like that. So let's do some pushing. Let's combine what we already know from, we did this when we wrote the print function. We used a for loop to visit each node. And then I'm going to have a brilliant idea and reuse what function we already wrote today, push front. Are you with me that this part will visit every node in the list? Okay? And then do you also agree that this will add one node for every node that was in the other list? Okay. Don't answer me right away. Well, then what's wrong with this code? It compiles and it runs. That's not the problem. I'll let you think for a minute. Okay. I will only accept an answer from someone who hasn't had a chance to speak up in class yet today. What's wrong? Yes, please. Oh, are we going to get the end right with p equals null pointer? This is a really tricky part of the code that led me to just say rainbows at the end. So I'm going to shift us away from that. Why don't you trust me that the loop really does visit everything and doesn't go off the end? It reverses the order. Yes. So if you push front on 1, and then you push front on 2, where should I put it? Right here. And then you push front, you get that. Okay, so I heard a very interesting solution right here, which my the instructor who taught 280 before me did it the way you suggested it, which was you were like, well, if you can reverse it, you can just reverse it again and you'll get the right answer. Yeah, you could. Yep, and that will get the right answer. Absolutely. Let's do something that's way more complicated than that. Oh, well, actually, what would be wrong? So the upside of reverse is you get the right answer. Another upside is that you can reuse the code that you already have, and you don't have to write more code. What's a downside? It takes more time. Why? Because you got to do it twice. Also, you call new a whole bunch of times, and new is kind of slow. So, wouldn't this be a lot easier? Wouldn't life be easier if we had pushback? Okay, let's just write it. So, how do we insert stuff at the end of the list? Let me tell you the worst way I can think of. You start here and you go oh, I found the end. Let's make a new one and then we'll make this one point here. That's actually the only way we can do it with the code we have so far. What would be faster than finding the end? Remembering the end or knowing where it is. How could we possibly do that? We have pointers and we can store pointers. Well, do we want to store this in the list or in the node? We store it in the list. All right. First and last. Come on, this is my list, and it's a private member variable. I do what I want with my private member variables and private member functions. So we add another pointer, and it points to the last node in the list. Okay, there's our representation invariant. So now here's what the picture looks like. So first points to first, just like it did before, and last points to the last node. So let me first be upfront with you that I am creating bugs. push front and pop front now have bugs in them because they need to deal with the last function. Or sorry, the last pointer. Also the constructor, that's got a bug in it. We have to initialize this. So when you add a member variable, you really got to make sure every single member function gets it right. So I'm only going to write pushback in this lecture. You'll get to do all of them in Project 5, so you'll get lots of practice. So we got to create a new node. This is similar to what we did before in pushfront. So that's this code. Then we got to handle the empty list case. And why aren't my pictures changing? If the list is empty, then we're going to have one node in the future list. So that means first points to the same place as last points to, and they both point to P. So otherwise, if we had multiple things in the list, it's a different story. Then first is all good already, and we patch up last to make it point here. So see how we have two cases? It matters whether the list is empty for this function. Remember my advice earlier in lecture, when you're working on project 4, test it when it's empty, test it when there's one, and test it when there's several. This is an example where it matters. Because we're running short on time today, I'm not going to dwell on the implementation of this. You can use this as a starting point. When you're working on the linked list in Project 5, you can start with the code from this lecture. So now that pushback is done, push all just works. All right. I am going to use push all and pop all to implement these functions now. So the destructor. Destructor should delete every node. So pop all calls pop front, and pop front calls delete. So in this way, function calls function, and eventually all the nodes are gone.
Why don't we just put the pop all function into the destructor? Because where would we use that?
So why are we writing pop all? Why not copy paste the code here? Because, next slide. We're going to reuse it. Before we do that, let's do copy constructor. So the copy constructor needs to initialize the member variables. How many member variables do we have now? 2. And if I have an empty list, first points to null pointer. If I have an empty list, last points to null pointer also. So then push all uses the loop like we did in the print function. And then it calls pushback, and pushback calls new. And so in this way, we eventually get a copy of all of the nodes. So we get a copy of all the nodes. So there's our copy constructor. So now here's why we wrote push all and pop all. The overloaded assignment operator deletes everything and then copies everything. This is good cheat sheet material. The beginning and the end of an overloaded assignment operator all look the same, no matter what the class. Yes?
So when we're writing a copy constructor, the stuff before the colon for the initializer list has to be the same, except maybe changing the data type. But we can have whatever we want after the colon.
So the question was about this part of the code or this part of the code?
Top part.
The top part. So this is the initializer list. Initializer lists go with constructors, and initializer lists are for member variables.
Right. Is that part of the copy constructor syntax, or do we have to, like, we make that initializer list do?
Oh, you can make that initializer list do whatever you want.
Okay, so only the part before the colon has to match exactly.
So the parts that matter, this is the part that says, hi, I'm a copy constructor. The only thing you'd change if it was a different type would be the type.
And you can keep other, or can you change other as well?
This is a variable name, so you can choose whatever you want. Other makes a lot of sense to me.
There pretty much is only one direction you can go in an int list, correct?
Is there only one direction you can go in an int list? Yes, good observation. You can go forward or, well, forward. So what about pop back? We implemented pushback. Why not pop back? Because if we remove from the end, then how could we find, if you have a pointer to this guy, how are you going to find this node? The only option is to go forward and find it, which is slow. Wouldn't it be nice if we could just say, oh yeah, that's my neighbor to the left? Yeah, so let's add that. This is called a doubly linked list. The nodes point forwards and backwards. And this is what the new pictures would look like. With first and last and null pointer. And this is what you'll do on project 4. And we're out on time.